Welcome to today's episode. We're diving deep into the fascinating world of data structures with a special focus on B-trees and a groundbreaking concept known as cache-oblivious structures. As we journey through these topics, we'll unpack their performance implications, design considerations, and how they adapt to the ever-changing landscape of computing hardware. Let's start with B-trees. These structures are incredibly popular in databases and file systems, mainly because they handle large datasets with impressive efficiency. The design of B-trees is all about minimizing the number of disk accesses needed to retrieve or update data, which is crucial for performance. Several factors influence how well a B-tree performs, such as the size of its nodes, how well they align with cache lines, and various other configurable parameters. It's essential to tune these elements carefully to optimize performance, especially when dealing with systems that have different memory hierarchies. In a typical setup with a two-level memory hierarchy, B-tree nodes are stored in disk-resident pages. There's a page cache in main memory that allows for quicker access to these nodes. So you have this interplay between the fast but limited page cache and the slower, larger disk storage. This two-level structure simplifies the design of algorithms, since developers only need to think about these two specific memory levels. However, traditional B-trees do face some challenges, particularly with modern storage solutions like solid-state drives or SSDs. One major issue is high write amplification, which happens due to page rewrites. Additionally, B-trees can have significant space overhead because they reserve extra space in nodes for future writes. These inefficiencies have sparked interest in exploring alternative structures and optimizations. This brings us to cache-oblivious data structures, a revolutionary approach that aims to deliver optimal performance without the need for tuning parameters for specific hardware configurations. So, what does it mean to be cache-oblivious? These structures are designed to work efficiently across a variety of machines, no matter their underlying memory hierarchy. By abstracting the complexities of cache sizes and disk page configurations, cache-oblivious algorithms can keep the number of transfers between different memory levels within a constant factor. Cache-oblivious structures effectively leverage a two-level memory model while also capturing the advantages of a multi-level hierarchy. They strive to maximize performance by operating as much as possible at the highest cache level. This is particularly beneficial in environments where hardware configurations can vary widely, allowing algorithms to maintain high efficiency without needing extensive modifications. One interesting implementation of cache-oblivious structures is the Van Emde-Bos layout. This layout combines a static B-tree with a packed array. Here, the B-tree is constructed by recursively splitting the tree at the middle level of the edges, resulting in subtrees that are square root in size. The innovation lies in storing each recursive tree in a contiguous block of memory, which promotes efficient access patterns. To support dynamic operations like inserts, updates, and deletes, cache-oblivious trees utilize a packed array structure. This structure uses contiguous memory segments to store elements while leaving gaps for future insertions. By spacing these gaps based on a density threshold, the packed array can accommodate new elements with minimal relocations. However, if the array becomes too densely or sparsely populated, it will need to be rebuilt to adjust its size. The static B-tree acts as an index for the packed array, requiring updates to ensure it accurately points to the correct elements. This innovative approach allows for efficient on-disk structures that can mimic the performance characteristics of in-memory data structures. However, it's worth noting that as of now, there are relatively few non-academic implementations of cache-oblivious B-trees. Despite the theoretical advantages of cache-oblivious B-trees, practical implementation challenges remain. One major concern is that even though cache loading is abstracted away, the negative impacts of paging and eviction can still affect performance. Plus, when it comes to block transfers, the complexity of cache-oblivious B-trees is comparable to that of their cache-aware counterparts. However, advancements in non-volatile byte-addressable storage devices might shift this landscape, potentially leading to more efficient implementations. In the realm of traditional B-trees, various adaptations have emerged to address their shortcomings, particularly concerning SSDs. For example, lazy B-trees like Wired Tiger and LA trees use in-memory buffers to reduce the number of I/O operations by buffering updates before they're written to disk. This strategy minimizes write amplification and enhances overall performance. Another innovative solution is the FD tree, which embraces immutability by storing data records in immutable sorted runs. This design helps limit the size of mutable B trees and reduces space amplification. Similarly, BW trees tackle space amplification by keeping separate on-disk locations for B tree nodes and their updates, leveraging a log-structured store for persistence. This design not only reduces write amplification, but also eliminates the need for latches to protect pages from concurrent access, making it a compelling alternative for modern storage systems. As we wrap up, it's clear that B-trees are still a foundational data structure in the world of databases and file systems. However, their limitations in modern environments have led to the exploration of cache-oblivious structures and innovative adaptations like lazy B-trees and FD trees. As technology continues to evolve, the need for efficient data structures that can seamlessly integrate with varying hardware configurations will only grow. By understanding these concepts, we gain a better appreciation for the ongoing advancements in data structure design and their implications for software performance. Thank you for joining us today as we navigated the intricacies of B-trees and cache-oblivious structures. We hope this discussion has inspired you to further explore the exciting world of data structures and their applications. Until next time, keep learning and stay curious.